We're going to extend our discussion of current by talking about how current flows through objects. Now, the current that flows through most substances, especially conductors, is directly proportional to the electric potential applied across it. Now again, electric potential is when you set up one side of a conductor to a high potential and the other side to a low potential. Positive charge wants to move, and we pretend the positive charges move. Positive charge moves from high potential to low potential. Think of it like rolling downhill. So the current in a material is proportional to the voltage. Higher the voltage, the higher the current. Now this doesn't apply in all materials. Some materials, especially some electric circuits called diodes, are specifically designed not to follow this trend. But in most conductors, so copper wire, aluminum wire, and so on, and most of the things we'll be working with for homework problems, follow this relationship. Now, how are these related? This is proportional to. That's what this symbol means. It looks like an infinity with part of it cut off. It's not equal sign, right? These are not directly equal to one another. They're related. If you double the voltage, you double the current approximately. If you triple the voltage, you triple the current approximately. So how are they related directly? Well, there is a term called the resistance of an object that relates these two features. The resistance of an object is the slope of the line between the voltage and the current, given this equation. The voltage is equal to the resistance times the current, or sometimes the current and the resistance are flipped. Again, you know, the commutative property in algebra, we can easily flip that and say V is equal to I times R. This equation is famous, and we'll be using it quite a bit. This specific equation is typically called Ohm's law. Ohm's law deals with the resistance, again being the slope. So think of this like an algebraic equation. Y is equal to m times x, where m is the slope of the line. In this case, the resistance of an object is due to the physical makeup of that object, like the capacitance of a capacitor was due to the physical makeup of a capacitor. If I give you a resistor of a specific value, that's the value of that resistor. That doesn't change. But knowing the value of the resistor, if I place a potential across it, you can tell me what the current is. Or if I want a specific current through the resistor, you can tell me what potential is needed to get that current. Now, in materials where this equation is obeyed, where if you plot current versus voltage, the slope of this line is the resistance. So high slope means a high resistance material. Low slope means a low resistance material. That means you don't have to apply much of a potential to get a large current. So the resistance you can think of as an intrinsic resistance to the flow of electricity in a material. So materials that are resistors, that are insulators, right, have high resistance values. Plastic, for example, has a very high resistance. The air has a very high resistance. So these are things that have very high resistive values. So you need a very high potential to have a current go through them. And then there are materials where charge flows very easily. We call these conductors. Conductors have very low resistance values. Copper, aluminum, and so on. These metals have very low resistance values, so it doesn't take much of a potential across it to get a large current. Materials that obey Ohm's law, that obey this linear relationship, are called ohmic materials. And most materials are ohmic. But again, you can design specific materials or specific devices that don't follow Ohm's law. We won't be getting into those in this class. Now, resistance value, it has to have a unit, right? We know the potential here is in units of volts. We know the current is in units of amperes or amps. What is the unit for resistance, the SI unit for resistance? Well, the unit of resistance is called the ohm, after the scientist Ohm who came up with this relationship. We don't use O's though for units, right? And a big O looks too much like a 0, so it would not make a good unit. So instead of an O for ohm, we use the Greek letter omega, which is kind of like a horseshoe that flares out on the bottom. This Greek letter omega, whenever you see that, think ohm. That's the resistance unit. For 1 ohm, if I solve this equation for resistance, divide both sides by I, R is equal to V over I, or 1 ohm is equal to 1 volt over 1 amp. So when you look at resistance values, if you go to a store and you buy a bag of resistors, again, Radio Shack is a fading example of this, but there are electronic stores where you can go in and actually buy resistance values. Those resistors have a fixed resistance, and we'll talk about how to calculate that in a little bit. Lastly, drawn on the bottom here is a very simple circuit where I have a battery and a resistor. So a resistor, again, is just typically a resistor is a conductor that has a specific resistance to the flow of electricity. We pretend that the rest of the wires in this circuit are perfect conductors, that they have 0 resistance. That's not true. Only superconductors, and we'll talk about those later, have 0 resistance. We're going to pretend that these are superconductors. But the resistor here, R, has a very specific resistance to the flow of electricity. 10 ohms, 100 ohms, 1,000 ohms, 550 ohms, whatever. When I hook it up to a battery of a given potential, current flows through this completed circuit. How much current, in this case it flows clockwise, from the positive terminal of the battery through the resistor back to the negative terminal of the battery. So from high potential through the resistor to low potential. So current flows clockwise. The same current has to flow through this whole circuit. Think of it like water flowing through a circular tube, right? Water doesn't magically appear. There's no point in the tube where suddenly you have a lot of excess water flowing compared to the rest of the tube. Current doesn't disappear. So the current I is the same throughout this whole simple circuit because it's just one loop. How much current goes through this circuit? Well, if we know what the voltage or the potential in volts is of the battery, and we know what the resistance value is of the resistor, if we know potential V and we know resistance I, we can solve this equation, resistance R, sorry, we can solve this equation for I. We can calculate what the current is in that simple circuit.